What's up, everyone, and Happy New Year. Been a while since I made a video, but I have been busy on a time tracking app that we're working on at loop speed. I'm really obsessed with time. It's our most valuable resource, and the kind of goal there is to help people understand how they're spending it, make more accurate estimates, etc., etc. Plus, I've been busy with some other stuff, so not had time to actually record anything, but I put aside a few hours today and I'm going to be working through this new blog post of mine, which is building this Three.js powered animated wave plane. It responds to scroll, which is pretty cool. You can turn the grid on and off and adjust the grid size, as well as play around with some color palettes. So yeah, let's get started. This project will help you learn more about Three.js shader materials and setting them up in a Next.js Typescript app. As I showed at the beginning, we'll also be adding some scroll interaction using GSAP ScrollTrigger, which will give the impression that the plane is moving backwards and forwards. I'll assume that you've got some basic React knowledge and that you have a Next.js project set up using TypeScript and Tailwind, although that's not essential. All right, we'll go ahead and install the dependencies then. We're going to be using React 3 Fiber, Dre, which has some useful helpers. As I mentioned, GSAP for animation and GSAP React for using GSAP in React. We've got a color package, some loaders for loading our shader files within Next.js, GLSify for importing within our shaders, and a noise module which we'll use to kind of procedurally generate this terrain. So the packages have been installed, which is good. We're going to need to create a shader or some sort of TypeScript declaration file so that it doesn't throw errors when we try to import our GLSL files. So we can put that in the root. That's that done. It just tells the system that to treat those imports as strings. We're now going to need to update our Next.js config, and this is going to bring in some of the packages that we just installed. So we've got raw loader for loading the files, GLSify for transforming them, and GLSify loader for loading those with GLSify. Next up, we have the kind of canvas setup, which is the most outer React component for the 3 scene. So I'm going to create a new file for that. Let's call it wave canvas, wave plane canvas. Let's stick with this. And I'm going to copy this in. So we'll note in Next.js, components are server-side by default, so we need to mark it as use client with this directive at the top here. We've got a kind of camera and some values on the camera. The far value will tell the renderer at which point to cull any objects in the distance. And we're not planning on making the plane ginormous, so we can sort of play around with the lowest possible value there to maximize performance. We've got alpha off, we're not having a transparent canvas, and we've got anti-alias as false as well for performance. Attached a black background to it, and now we're ready to set up our component. Okay, so building the wave plane component, it's really just a plane that's rotated 90 degrees on its x-axis. So create a new component for this. We are grabbing the viewport size from the use3 hook, which only works inside our canvas. Can now fix this import. Take this out. Okay. And then the width and height are multiples of the viewport width and height. And then the size, because it's a square, is just whichever is largest across between those two. The segments, it's worth noting that the plane segments form these arguments within the plane geometry, and those add more vertices. And so if we want to have a smoother wave, we'll increase the number of segments. So I've done it as a multiple of the size here. And if we set this to 0 or 1, then we wouldn't be able to see any distortion when we get to that point. So what we have is our mesh with the plane geometry and then a basic material, which will color it gray. And so if this has all worked, I'll bring the canvas into my page. What we should see is a gray. Let's load it up. Yeah, so we've got a gray plane angled here. It's been rotated minus 90 degrees on the x-axis. The canvas, though, doesn't have the correct sizes on it to take up the full screen. So if I do that, now we've got our plane. So this is really the basis for the rest of it. I've used the use memo hook here to prevent these values recomputing when parent components re-render. So we're only going to be responding to the viewport width to calculate the plane width here. And yeah, we've got this result in our new app. So we're on to the custom shader material now, which is what we'll use to give it some depth, and that will be part of the Vertex shader. And we will color it based on that terrain height or depth using the fragment shader. So if you are completely new to shaders, this is some prerequisite kind of high level knowledge, but I encourage you to look at some other resources like the Book of Shaders, and I'll put some links in the description. The main kind of concepts which you need to understand are input variables from which we pass from our React component into the shader are called uniforms, and they're given that name because they are the same for every single pixel that's been calculated within that shader. In TypeScript, we can create a type to define these uniforms. We can set up type for our custom material as well, which we'll cover in a moment. The Vertex shader can be used to transform the vertex positions, and so it's primarily used for kind of changing the shape of things, moving them. Can also be used for manipulating points or particles. And in this one, we're going to use a noise algorithm to kind of create that organic wave where we'll be displacing the Z part of the vertex position. The vertex shader runs before the fragment shader, and so it can pass data via varyings to the fragment shader. So we can calculate the height of the wave, and then we can pass that value to the fragment shader as a varying. And the fragment shader is executed in parallel, much like the vertex shader, for each fragment pixel on that geometry. And so it's a different paradigm to working with CSS or JavaScript styling, because the function's running individually for every pixel in parallel, and you have a coordinate which is the pixel's position, say, on that plane. So with that coordinate, you can color it differently, and you can also use the varyings or uniforms to compute a final color. So vertex shader, distortion, fragment shader, coloring, that's sort of how we're going to be using those in this project. In my blog, I've included a default vertex shader, which is typically used for kind of 3D objects in a 3JS scene. It's been heavily annotated. We're going to use this as a basis, and then we're going to add to it. The kind of main takeaways are that it has to set a GL position, and it can also pass through a varying, which needs to be defined at the top. So we've declared that we want the VUV, so varying UV coordinate, and then we're setting it here. The UV's just passed into this from 3JS. The rest of it is calculating the position within the scene. So what we're going to want to do is displace the vertices along the z-axis. The plane would initially be like this, and so the z would be towards and away, but because we've rotated it, z will now be kind of up and down, which will give it the desired effect. We're going to be using the GLSL noise package that we installed at the beginning, and a simplex 3D algorithm from within that. The noise function's really useful for kind of these organic looking effects, such as cloud, terrain, and waves. And when we call that function, we can pass in the position of the vertices and get a different noise value depending where on the plane we are. So, but it will kind of smooth out gradually, and we won't get any jaggedness. So I'm going to copy the vertex shader code into our waveplane.vert file. So the .vert file type is just .vertex or vertex shader. This could also be GLSL. Our shader config set up to support .frag.vert as well as GLSL. So the noise function is imported using glsify, which is one of the packages that we installed and we configured in Next.js. So without this, that won't work. And you can find the source code for a noise function, paste it in here, and then keep it inside your file. But this is just a neater way of doing it. Okay, so we're going to cover the uniforms in a bit. main thing is these are all the same as the sort of boilerplate Vertex shader, but we are calling our noise function with a noise input. So we've defined a vector3, which is a 3-part variable, which is used for X, Y, and Z position, and then inputting the position with a division on it. We can play around with these values to see how they affect it in a minute. The scroll progress is covered later, and the time, by passing the time in as the third vector3 value, the noise will constantly move. So if we took this out and just had a static value, it wouldn't be animated. And then we are computing the n value from the noise function. We're normalizing it. So we are changing it from the range of -1 and 1 to 0 and 1. We do that by timesing it by 0.5 and adding 0.5. We're declaring a new position, which is initially set to the incoming position, but then the Z value has the N value added to it. So we take the original position and we add our noise value, which is between 0 and 1. So at some points it's not going to have changed, and at other points at max it'll be at one additional Z value. And then we've defined our varying. So we want the UV coordinate for the fragment shader to know which pixel it's shading. And we also want to pass through the terrain height, because we can use the terrain height, which is the noise value, to color it appropriately. So that's the Vertex shader. We'll kind of have a play with some of these values in a minute once we get the rest of the custom shader set up. So I've covered these points here, but please do visit the blog if you want to take another look at these. So as I mentioned, a basic fragment shader needs to output a color. So what we can do is create our minimal fragment shader, which we'll call waveplane.frag. It needs to output a vector4, which is an RGBA value. In this case, the red, the green, and the blue are all 0.5, so it will be a mid-gray at full opacity, or alpha. We'll come back to the fragment shader in a bit. Now, we need to set up the custom shader material and import our shader files, set up some uniforms, initial uniforms, and then create that waveplane shader material using the shader material from React 3 Dre. So I'm going to bring this stuff into the waveplane component. All right, so the uniforms that we'll want, or that we'll be using initially, are these ones here. All of the uniforms are prefixed with a U, so that in the shader code we can tell where they've come from. The color palette, these cosine gradients, are imported from @thing color, And yeah, check out that toolkit. It's really cool. But the cosine gradient colors will generate a different color when passed an input value between 0 and 1. So we can, which kind of lines up to our noise value. We have a noise value between 0 and 1, or terrain height. We can pass that in and then get a different color, a different gradient color. So I've got a default color palette, which is passed into the initial uniforms, which have 0 time, 0 scroll progress, grid showing, and a grid size of 24. Now we can create the shader material. So this is using our imported vertex and fragment shaders, and then it's made available using the extend function. And this is from React 3 Fiber. And we're declaring an interface type for this wave plane shader material so that when we add it inside our mesh, TypeScript will be happy. Okay, so we've got the material. Let's add the shader material code in here. Going to bring back in use frame hook. And this. Okay, nice. So we haven't got any TypeScript errors, which is good. The shader material has a ref attached to it of type shader material and our uniforms. Shader material is imported from 3. The use frame hook will run every frame, so it could be 60 times a second. If for whatever reason, the ref isn't attached properly, then it will return out. If not, it will update the uTime uniform with the elapsed time. So now what I'm hoping, if this has all been set up correctly, is that our plane will be moving. Yeah. So that's the vertex shader in action here. If we change our frag color, we get a different color here. So that demonstrates that that's working. The noise value, so if we were to take off the division by 4, so now we've got a much sort of steeper, rougher plane surface. And if we were to divide, say, 1 by 10, then it would be kind of more on one axis. So I'm going to leave this like this. If I take out the time value, we still get the distortion. It's just not moving. And if we speed up the time instead of slowing it down, it moves a lot quicker. So they're kind of like the basic ways in which you can influence the effect here. I forgot to mention the key. So the key that's assigned to the custom shader material enables hot reloading whenever the files are changed. So we saw that when I changed the color a moment ago. Okay, now we can move on to the color within the fragment shader. We've already touched on the color palette uniform, which is an array of 4 vector 3 colors. So in our component, we've defined an array of vector 3 elements, which is our default color palette. If you want to change the color palette, there are loads of options in here. So we could try this one. We're going to copy the fragment shader code into our waveplane.frag file, and then we'll update, we'll talk through that. First of all, I'm curious, does it work? So yes, it does. All right, nice. I've now added the uniforms up here. I don't think we're actually using time though, so time doesn't need to be within the fragment shader. The color palette we have in GLSL, you need to explicitly state how many items are in the array. So it's not like TypeScript or other languages where you do that. You have to declare it as having 4 items in that array. We've got a Boolean for showing the grid and the grid size, which we're not looking at yet. We've now added varyings. So we've got our VUV and our V terrain height. Our these are both set in the Vertex shader. A constant background color. This is going to be used to create the soft edges. See how we got a fade, sort of fading out in the distance and around the sides. So that's just set to black, which is a 0001. The cosine gradient color function has been taken from here. I didn't write this, but I came across it and thought it was really cool and worked nicely with the wave plane and the noise. And this will take in a T value and then the 4 colors. So we're going to call that function here to get our color as a vector 3. And we're going to pass in our varying terrain height, which will be between 0 and 1. And then we're going to pass in our color palette array values. So all 4 of those enter here. And then the final color, because we need to output a vector 4, we're just adding full alpha to the color here. And then in order to fade it out towards the edges, what we're going to do is use the distance function, which is a GLSL built-in method which calculates the distance of our current coordinate, which is an x and y value, to the center of the shape, which is 0.5, 0.5. Now, this distance can then be used in a smooth step function, which is another built-in method to generate a value between 0 and 1. And it will, if the value is less than 0.35, it will give us 0. And if it's greater than 0.5, it will give us 1. And then it will interpolate in between these 2 values. So if the value was 0.4, we'd be getting a value closer to 0. And if it was 4.9, it would be almost 1. It's a little bit confusing, the smooth step, but it's worth learning if you're not familiar with it, because it's great for kind of gradients and mixing of things. So this fog amount value is between 0 and 1. And then we use that value to mix our final color, our surface color, with the background color by that fog amount. We're just reassigning final color, the result of that mix, and then we output it here. So if we change these values, we can see how it affects it. So if I put this to say 0.1, we're bringing it in a lot. And 0, only the very center is at full surface color, and the black's bleeding quite far in. And if I do say 4, 8, it's a really fine, you probably can't even see it off of the edge there. You can play around with these values and see what you come up with. You see here, if the value if this value in the smooth step is greater than 0.5, we're actually seeing the edge of the plane because the max distance is 0.5, so it's not actually cutting it off, whereas this will ensure that no sort of sharp edges are visible. Okay, so that's the fragment shader, at least the basic fragment shader set up with the colors. And this already looks really cool, in my opinion. You can change the values here to get kind of different wave effects. So I could do, say, ×2 here. I've got this, which is quite cool. You can see how powerful the noise is with just a few simple transformations there. So if you did want the plane to fade out instead of to black, we could use our fog amount value to set the opacity, or the fourth value in the vector 4 to that, and then it would actually be transparent as opposed to pure black. Pure black works in this scenario because we have a pure black background, but if you had something behind it, you'd still get a sharp edge. So if you have a go and playing with that and see if you can get it to be transparent rather than faded to black. Just remember that you will need to set the material to transparent if you're going to do that. So that's in our wave plane. You need to set transparent to true. Okay, cool. So yeah, this is more like it. Next up, we can look at adding the grid lines, which will create that cool kind of techie retro effect. And we'll draw them with the UV coordinate and the grid size uniform. So we're passing in how many grid cells we would like there to be on our wavy plane. I'm going to copy in some of this code. We've got a brighten value function. This is in our fragment. The brighten value does what it says on the tin, which is increase the incoming float value by, in this case, 0.25, but it's clamped within the range of 0 and 1. So clamp, again, if you're not familiar with it, just means that the value will never fall out of these bounds. So the minimum is 1 and the maximum is, the minimum is 0, maximum is 1, which are valid color values. So if we passed in a color that was 0.9, it would just return 1. And we're going to use that to color the lines dynamically. Okay, so I'll paste in the code for drawing the grid lines. We are defining a line thickness, which is a value multiplied by the grid size, and it's multiplied by the grid size because it's going to be compared to a UV coordinate, which is multiplied by the grid size. So we use the fract method, which will give us the fractional part of that value. So if we passed in 0.5, which would be kind of directly in the middle, multiplied that by 24, which gives us 12. So we've got 12.0, and the fractional of that will be 0. And then we then want to basically determine whether that value is a line or not a line. And so we use the step function, and the step function returns a 0 or a 1, depending on if this value is greater or less than this value. So we've got 0 for this particular coordinate, and the line thickness is 0.0024. So this is less than the line thickness. So this step function will return a 0. And we're doing 1 minus because otherwise it fills in the wrong section. It fills in the bit that's not aligned. So we're sort of inverting it here. And so at this point, that would be a line. So right down the middle here, actually you can see we do have a line there because it's within the range of this. The fractional part is within this range. If we take off this, now we see that it's all filled with these are actually the horizontal lines. So now it's all filled. So the line, it's this bit here, but we don't want to color it like that. We want to invert it. So we do that for both horizontal and vertical. And then we will grab the maximum value because both of these are either 1 or 0. We want to always use the value when it's 1. So we'll get the max of those two. So it ensures lines get drawn in both directions. Then we get the line color using our brighten value function. We pass in the surface color for that particular fragment. We brighten the R, G, and B units, and we give it full alpha. And then we mix the final color with the line color based on the alpha. So we're either going to be showing the original surface color or the new line color based on whether the line alpha is 1 or 0. So when it's 0, we have the final color. When it's 1, we have this color, the line color. Yeah, and so now we have a cool looking grid, and we can adjust our uniforms in here. So if we made here, say 120, oh, my bad. The initial uniforms are being overridden by what's down here. Yeah, so now we've got loads of these, and the line thickness is always constant. So even if we have 8, we get same line thickness. Okay, cool. Next up, we're going to make the plane interact to our scroll. So yeah, to begin with, we're going to make sure that our page can actually scroll. So what I'm going to want to do is put a height class name on the element in our page. So in this case, this is 10 screens. We can check if that's worked, because now we've got a scroll bar over here. Okay, cool. For GSAP, we're going to want to make sure that we register the plugin, or in fact the 2 plugins within our component. So imported use GSAP and GSAP and the ScrollTrigger, and then registering those plugins within our component. So now what we can do is create a use GSAP hook. So the scroll progress is a ref that is going to be used to capture the kind of overall scrolling of the page, and the scroll loop will count how many times we've gone route That's cool. Actually, this is an incorrect dependency. We're not passing that in here. So the scroll trigger is created. It starts at the top and it ends at the maximum scroll position. When it updates, we're going to get the progress value, and then we're going to assign it to our scroll progress. And then in our use frame, we're going to want to pass that in like so. If we want to add the looping, so when we hit the bottom of the page, we want to then jump up to the top and continue, then we will increment our loop. So this will then go to 1. We'll set the scroll progress back to 0. So we're still at 1.0 at this point, but the window is right at the top. So that will give us a sort of smooth transition, because if we weren't keeping track of the scroll loop, it would jump to 0 and that would screw up the shader code because there'd be a sudden jump. But what we want is a sort of smoothly incrementing scroll progress value that means that the shader code will not have any sort of sudden jumps. Okay, cool. So it is moving slightly, which is good. What we might want to do is, well, two things. We actually need to add our scroll loop value here. So when we get to the bottom, it's working through. Because the value only ranges between 0 and 1, it's hard to actually see it having any effect. So what I've found is if you multiply that value by, say, the number of screen heights, it sort of tracks more closely. In fact, it should be there's actually 9 screens because the first one's visible. But now this should actually track kind of in line with the amount of scrolling that you're doing. Cool. I'm going to put this back to how it was. All right, nice. So let's just have a quick look in the Vertex shader, how that scroll progress value has been used. So we are adding it to our Y position, which offsets it. If we were to add it to the X position, you can guess what will happen there. Now we get movement in the other direction. I mean, we could add it to both X and Y and we'll get a diagonal movement, which is quite cool. Maybe move it in the other direction, like that. Okay, and then in the fragment shader, the scroll progress uniform needs to be added to the line position so that the grid line will move as well. So we've already talked about the wave plane vertex shader, but yeah, we can create a Y offset for our line. And you can add that on here. It's quite hard to tell what's happening with it moving diagonally, so I'm going to take off this. But yeah, as you can see now, the lines also move as you scroll, which is very neat. You've got infinite scrolling as well. All right, cool. So I hope you found this useful. The final result is on my website, where I've added controls that allow you to change the color palette, adjust the grid on and off. And you'll also see that there's this pointer movement. I've linked my full component code as well. So that basically adds the controls using the lever package, and that then sets up choice of palette, grid boolean, and grid size value, and passes that into the wave plane via props. Yeah, I really love working with shaders, and hopefully you will too. Peace.